we we were on primary treatment, and I think in our last class maybe we covered the SOR and this thing with this equation, isn't it?
Yes, sir.
So we covered SOR and only this equation. Am I correct?
Yes, sir.
Okay. So we start from here. Okay. Let's start. Now, here. Uh, I'm not very comfortable with this online stuff, but something is better than nothing. At least this is providing us some flexibility when we can't take a class. Otherwise, we have to look for a classroom, and in university it's very difficult, to a get an empty class. Take the makeup class, okay, empty classroom. Okay, so we covered up to this. That means the S1. What is S1? Now, let us assume, okay, suppose this particle, if it, if we want 100% removal, so what will happen? It will travel from point A to point F. I discussed it. Okay, so the vertical horizontal component will be V, that is the velocity of the flow, and the vertical component of the resultant Vs, we defined it as S1. I think up to this I covered. Okay, so
Yes,
this
sir.
is 100% removal. Now, let us assume there is another particle at this point. Now, if this particle is removed 100%, that means the resulting path will be from B to A, this dotted line. So again, horizontal component similar to the flow velocity, and the settling component, that means the vertical component, is VA. Now, if VA, that means it is less than S1. We know this is VS, this is the S1. We know. Now, if VA is less than S1, then what will happen? We know S1, this is the slowest settling particle, the slowest settling velocity. That is 100% removed. Any other particle with settling velocity lower than S1, it will not have sufficient time to reach from point A to A, or from this to this point, because its floating velocity is lower than the compared to the S1. So it will reach maybe probably to the outlet, so that means it will be washed away. So theoretically, you will say, according to this concept, okay, this particle will not reach from B to E. It will reach from, because since the VA velocity is less than S1, it will reach from point B to this outlet. So that means it will be washed away. Now, you have to consider the distance. Here, this particle, for 100% removal, it, it needs to cross a vertical distance of h. Whereas this particle, it needs to cross a vertical distance of h. That means height of the tank. Now, this h is definitely greater than h. So it covered a greater vertical distance compared to this particle. Since, be careful, please be attentive. Since this particle is covering a distance that is vertical distance that is lower than the distance that this SOR has to cover, or it covered, so we can say that due to lower or due to a lower magnitude of distance, it will also reach from B to F, because it has to travel, or it has to cover a lower magnitude of depth compared to this one. But if this particle, suppose if this particle was at this point or at this point, then what would have happened? Maybe it would have washed out. But due to this small distance, it will also remove from point B to, it will also travel from point B to point E distance. That means removal. Okay, now we know that according to this theory, it will not be if a particle, uh, if the settling velocity of a particle is lower than s1, that will not be 100% no. But here we are seeing that okay, some that this particle is removed. Actually, then what will happen here? The particles, some will be removed, some will wash away. Okay, some will remove, some will wash away. So some will be removed and some will be washed away. So what is happening actually uh, here? Partial removal is occurring, not 100% removal. Partial removal is occurring because due to two reasons. Number one, lower depth, and number two is the velocity is the velocity is lower than s1. So partial removal will occur. Now, what is that partial percentage? Let's see. Again, we clear all this stuff. We don't need this. Oh, oh, nice. We remove markings from this diagram, and then I think everything will be clear. Yeah. Now, you see, let us assume okay, the removal ratio, partial removal ratio is R. Now, this triangle, that means this is one triangle, this is one triangle with greater age, and this is another triangle, you see, with dual age. So R is equal to, we can write h by h, and h is the distance. We know s equal to ut or s equal to vt, whatever. So h is equal to this velocity va, and the time we assume t, and also this one vs, and same time is required because same time is required, although its setting velocity is lower than the this one, but same time is required due to this small distance max. Okay, it travels a greater distance, but it is traveling a smaller vertical distance. That's why the ultimately the time required to reach from to this point is same. So this t will be omitted. So this is the ratio Va by V. In this ratio, the particle will be removed at point B or in point adjacent or very near to this point B, for example, for here or for here. Okay. So this is the partial ratio. Now, one thing. Where is it? Who is knocking? Okay, class. So, what will happen? I am very happy that I think most of you joined. Almost 21 students they have joined. Thank you. Uh, you people are doing good. So, okay, let's continue. Uh, yeah. Now, we have considered, okay, for example, at this point or maybe at this point, we have considered only one particle. But actually, there are hundreds, thousands of particles. So, this removal ratio, we will introduce an integration. That means there are many particles in this one. Okay, that's why we have introduced an integration. Now, let us assume, okay, total number of particles, for example, 100% total number, or maybe in round, in full digit number, we consider one total number of particles. Okay, now y0 what happened to Tariqul Islam? I already admitted you. Now, this is the full proportion, that means total amount of particle, that is what. Now, this is the proportion or amount of the particle whose settling velocity is less than S1. So, this particle theoretically maybe will not be removed. But we know, so now we want to, and so this is the proportion that theoretically will not be removed. So if we want to find out the removal percentage, let us write it as F. Removal percentage is, this is the total number of particles. So removal percentage, this is, we are assuming that this proportion will not be removed. So this is the total and this is not, this will not be totally removed. So total removal will be 1 minus Y0. That means the 100% removal. And also this proportion will come, VA by VS plus VA by VS, because this is also being removed partially. Some is removed and some is not removed. And here we are trying to compute the total percentage of particles that have been removed by the sedimentation tank. Now we need to put some limit, definitely, because this is integration. So 0 is initial amount of particle and Y is the proportion not removed. And this is dy here. And we integrate, and this is the equation. If we use this equation, we can find out how the proportion of the particles that have been retained or that have been removed by the sedimentation tank in percentage. And in the very next problem, we will see. Now, my question is, did we understand the overall theoretical concept here? Nobody is answering. Hello?
Yes, sir.
So should I move forward?
Yes, sir.
Thank you, thank you. So this is the example. In this example, we will apply this equation. Let's see. Okay? We will go to the book. I have a soft copy of the book, but that is for myself, for my use only. According to the law, I cannot give and I do not break the law. But what's the point? It's already available in Nilkit. Okay. Now, who is it? Yeah. Let's see. Who's trying to enter in our class? Mr. Sadnam. Hello, Mr. Sadnam. How are you? Maybe he's sleeping. Okay. Yeah. This is the an example. Let's go. So this is a clarifier. Here you see a clarifier, or we will design a primary sedimentation tank. The SOR is given with 30 meter cube per meter square per day. And they have asked us, or the problem is asking us to quantify the removal percentage, that means F, follow with this data sheet. So this is the sieve analysis. These are defined particle size retained by defined sieve, sieve, and this is the size, proportion of the particle of the size less than this proportion. So 10% of the particle, they are having size greater than 0.1 millimeter. So 20% of the particle have size greater than this diameter. So these are defined diameter and the proportion are given greater than the retained size. Very uh, common concept from engineering materials, or I forgot whatever is the book. Maybe I studied it 26 years ago. I don't remember, but I think as, as far as I remember, it should be in engineering materials, isn't it?
Yes, sir.
Yes, sir.
You see, I studied, I think, in 2000, in the year 2000. And then I didn't see. Okay. Now, problem with the, if you want to solve this problem, you need to know some data. Otherwise, you cannot solve this problem. Number one, data, it must be given in the problem. The water temperature, or the temperature of the water, and the specific gravity. These data must be given. Otherwise, it is impossible to solve this problem. Definitely, these data will be given, maybe tabular form or directly, whatever. If these data profiles are given in tabular form, for example, 20 and 25, you can interpolate the required temperature, or the data would be directly given. Yeah. So from the data, we know how we get this data. There are many tables and define parameter with respect to temperature and other stuff. These are given. At 15 degrees centigrade, the kinematic viscosity nu is this, and specific gravity of water at 15 degree is this. Now this is the Stokes equation. We know. We already went through it. So we know this value, the specific, the density of the particle should be given here. It must be given in the problem. So we write it in kg meter cube per second to be converted, and then the density of water, this is 0.990. Okay, specific gravity, and we converted it to all this stuff, and this square and kinetic viscosity directly given. So we get this equation, but the variable here is diameter. We do not know. But again, the diameter is given here, particle size. So we construct this table, we put this diameter. So these two columns are directly from the given data. And now we will consider the compute the settling velocity of this particle. Now, for let us consider this example, or maybe no, this example, first example. We delete it. This one. Yeah. So for example, for 0.1 millimeter diameter, we put it here. But remember, this is given in millimeter. So we here one example has already been given for you. So 1 millimeter we convert it to meter. We put it here. We get meter per second, and again we convert it to from meter per second to millimeter per second, and we write it. Okay. Similarly, for other diameters, we put it here and we get these values. Okay. Now, the SOR is given, surface overflow, that is 30 meter cube per meter square per day. So this is the SOR 30 meter cube or 30 meter per day, whatever, and we convert it again to millimeter per second. That is similar to this unit. Okay. Now we also know the S1. Now we draw a graph. This should be millimeter graph. Here, if I go to the PowerPoint, I want to draw something. Here. So what we do, we draw a graph. It's millimeter per second. That is settling velocity. And this is fraction less than the stated velocity. That means if 80%, 10% is greater than this size, then 90% will fall within this size. Isn't it? So This is the fraction of particle with less than the stated velocity here. Now, if size here, 10% size is greater than this velocity. So 90% will fall within this range. Okay. So here for the first plot, we see 0.34 here, 0.34. No, what is that here? 0.969. This is the 0.969 and less than the stated velocity. That means 10% is greater, so 90% is less than the stated velocity here. This one, 90%. So here we get one plot. Then again, for this one, 0.620 here, 0.620, and it will be 80%. So 0.8 here. This is 0.8. And then we draw, we get an S curve. Remember, it must be an S curve. It must be S curve. Okay. So after we draw this S curve in a millimeter graph, then our next objective is to find the SOR. We know SOR already. We calculated here. If you remember, it's given in the question. SOR. We converted it from millimeter. Sorry, from meter per day to millimeter per second. And now, here again you see, here, somewhere SOR, this is 0.34 millimeter. Here. So, this is y0. So what happened? The region equal to what is happening? So what will happen? The particle with velocity equal to SOR, greater than SOR. So in this region, it will be 100% removed. Okay, we know. But this will be this region. It will be partially removed because setting velocity is lower than SOR. So in the proportion, if we remember, VA by VA. So we need to integrate it according to our formula, VA by VA. Yeah. This formula, VA by VA. Okay. So how we do it? Here, I'm showing you. I again draw a graph. And here. So this is the region we will integrate. Definitely, this is the curve. So here, this is 0, and the intersection, the horizontal intersection here is this point. So it is 0, it is 20, 40, you have subtracted, you will find somewhere around 29.7, the intersection at y-axis. So this is, let's write it, 29.7, or dividing it by 100.297. Now, we need to integrate. That means we need to convert it into, divide it into several slices. For example, now the first slice, again, a clear picture. Yes. So this is 0.297 and this is 0. So let us assume this is the first slice. So the value of the first interval of the first slice, 0.05. So we again another 0.05. So the 1, 0.05, 1, maybe a bigger. Yeah. 0.297 and this is 0. So the first slice interval 0.05, again 0.05, so 1, again 0.05, 0.15, again 0.05, 0.2, again 0.05, 0.25, and then we cannot go because the upper limit is 0.097. So this one will be 0.047. Okay. Now we have here. So this del y, these are the value of the slices here. These are del y. Okay, because according to the equation, we need to find out this value via del y. Vs we know as well, via del y we need to compute. So that's why we are uh, uh, slicing or dividing this curve. Where is it? Yeah. So these are del y. So you see here del y, so 0.0505050507, and the last one is 0.047. Now, from how can we compute this v value? So we know we need this v. What is this v? Let's see. Actually, this v, for example, for the first slide, the upper end, for the uppermost slide, these two ends, we select a midpoint here, a midpoint, and then we draw a perpendicular. And what is the value here? Let's see. If you draw a perpendicular here, maybe the value somewhere around here, you see 0.31. So here it will be, the value will be 0.31. Again, for this one, the middle point, we again go downward, vertical. And this value is here, 0.27. So again, we choose the midpoint for each slide and we go perpendicularly downward and or vertically downward, and then what will happen? We get these values. Yeah, we get these values from the x-axis in velocity. So now v del y, for example, 0.05 multiplied 0.8, we get this product. This value from the product of 0.05 from the product of first two rows. We get these values, and then the summation of, the summation of v del y, this is the summation of, not this one, summation of, let's forget about it. So this is the summation of 0.04, 0.03, 0.08, 0.01, 0.02, 0.0. This is the summation. Now we can use this equation. We know 1 and 0 is 0.297. So 1 minus 0.297, this value. V del y, this value, and Vs is the SOR. And the SOR is 0.34. So we put it here, and the solid removal percentage is 90%. This is the solution. So this sedimentation tank that we are designing, it will remove 90% of the solid. Is it clear?
Yes, sir.
Okay. Hold on for a moment. Okay, so any problem? Any? Did you completely understand that problem? Any confusion? Please, for any confusion, please ask. If you have any confusion, do you have any confusion? ওই সবাই চুপ কেন? Is it clear?
Yes, sir. No problem.
Okay. So when we are having our next class test, or did we already take our class test? I think we already took our class test, isn't it?
Yes, sir.
Okay, so we don't have it now. We will only continue our lecture. Okay, so we move on towards our next topic. Let's see. Okay, and this was the example that I showed right just now. We don't need these two slides, like setting column analysis, this slide and this slide. We don't need in this course. But we need this one. That means the design of the rectangular sedimentation tank. Okay. Now, these are some information that I will give, but please do not memorize it because we will need it for our design purpose. And that design equation we will see, inshallah, in our next class. So these are just information. Okay. So number one, these are the parameters that you need to know. The value of the parameters, it must be known to you before you approach to design purpose. So number one design parameter is SOR, or surface overflow rate. Now we are considering rectangular sedimentation tank. And these are all given in your book, chapter 5. So the SOR, the range will be 24.5 to 49 meter cube per meter square per day, depending on the application. And the side side depth of the say rectangular sedimentation tank, it should not be less than 3. So a minimum value of 3 meter of depth must be provided. And the detention time or the wastewater holding period by the tank, it will range between 1.5 to 2.5 hours. But if you provide shorter retention time, for example, 0.5 to 1 hour, what will happen? Within this time period, solids, they won't be able to reach to the bottom portion. So many solids will escape due to shorter retention time. That's why we provide 1.5 to 2.5 hour of retention time. Now, wire loading rate, we know if the wire loading rate, particularly in the outlet, what will happen? If the wire overloading a wire loading rate is substantial, we know, we have seen, I informed you in my last class that if the wire loading rate is very high, then what will happen? Turbulence will be created in the outlet zone, which will extend backward in the settling zone. And once the turbulence is extended backward in the settling zone, then the solids that were previously settled on the bottom of the tank, it will rise. That means failure of the system. So we need to control the wire loading rate. So this is a very important parameter. So wire loading rate, here the guidelines are given. It must not exceed 250 meter cube per day per linear meter. That means for every linear meter or for every meter of where the loading must be 250, must not exceed 250 meter cube per day. When that overall treatment plant is designed to receive a flow of 3785 meter cube per day. Okay. Is it clear?
Yes, sir. It's clear.
And if the wire flow, inflow rate it exceeds it is greater than 3785, that means greater than this value. This loading rate is for this value. Now if the flow is the overall flow in the treatment area is greater than 3785 meter cube per day, then wire load must not exceed 373 meter cube. This will be per meter square, not day square. This two will come here. Meter square. We should be something. So this will be this one, meter square per day. So there are two criteria. One for 3785 meter cube per day flow of overall treatment plant, and the flow exceeding 3785 meter cube per day. Okay. Now, another important topic is scour velocity. What is scour velocity? So, scour velocity, it is the horizontal velocity of the flow that causes resuspension of the settled particle. Now, we need to avoid resuspension because in the sedimentation tank, what will happen? Solid will settle, it will not be resuspended. And scour velocity, it is that horizontal velocity that causes resuspension of the settled particle. So, definitely, scour velocity must be avoided. And how we can compare scour velocity? This is the horizontal velocity that causes scouring. So we need to compute this value. So VH is equal to this equation, and the expression of the symbol definition of the terms of the variables are given here. For example, this is the horizontal velocity that will cause resuspension. K is the constant of the material, of the solid. S is specific gravity of the solid particle, which will be scoured. G is expression, those particles of the diameter of the solid particle, and F is Darcy fraction, Darcy wastewater friction factor. This ranges between 0.02 and 0.03. Okay. And we will apply all these concepts in our next one. And this is the BOD TSS removal rate of our design sedimentation. So this we can compute it mathematically and also by graph. So this is the mathematical equation, R is equal to T divided by A plus BT, where R is removal efficiency in percentage, T is the detention time. We can get it from this range, and A, B are constant. Here we will get it from our table. This is the table. This is the BOD, because we know sedimentation tank is designed mainly for TSS or total surface of solid and some particular BOD removal. So for BOD, the A and B constant values are given, and for TSS, A and B are given. From this table, we take these values. If we put it here, we get the removal efficiency or expected removal efficiency of a sediment tank. We can also compute it graphically. How? Here, for example, if we know the SOR, for example, from this range, for example, let's say we have assumed SOR to be 30 millimeter per day. So now, or maybe here, 40 millimeter per day within the range. So this is the 40 millimeter of the SOR. We move forward, upward, and then here, this is the BOD removal percentage, 32%. Somewhere 58%. So we can compute it graphically, and we can also compute it with the equation. Any approach that will work. Okay?
Yes, sir.
So these are the design criteria. We will use it inshallah in our next class. Now, I want to talk about another sedimentation type, that is circular. So far we talked about rectangular. Now we will talk about circular sedimentation type. Actually, the main concept or principles are saying there are some major differences we will see. For example, this is a circular sedimentation tank. I am not good. Maybe I draw it as cylindrical. Okay. So in circular sedimentation tank, what will happen? Flow will be distributed radially. That means in the direction of radius. Whereas in rectangular sedimentation tank, flow was distributed horizontally in the settling zone. But here, flow will be distributed in the direction of radius of the tank or diameter of the tank. And definitely this will be, for example, settling zone. For example, this is the inlet zone. There will be, we will see later, settling zone and outlet zone. Okay, so again, what will happen? Flow will be distributed radially, and solids will settle on the bottom of the tank, and it will move, and the solids that are wastewater free of solid, it will move towards the outlet. Here, there is a rectangle, circular sedimentation tank. Flow is distributed radially, and these are V naughts. These are V naughts. You see, and flow is moved after solids are removed. It is passed towards the outlet. And this is a bridge. It provides you access. If any equipment or if any part or if any component of the sedimentation malfunction, you have access. You can go and you can fix it. Otherwise, if you don't put it here, you will swim. Maybe it's your choice. So, how the flow is distributed here? By baffle valve. Maybe it will have perforated baffle or perforated hole, and flow will be distributed. And this baffle valve, it is designed to be 10 to 20% of the total diameter. For example, this is the tank diameter D, and it will be 10 to 20% of the total diameter, the width. And extending 0.9 to 1.8 meter below the water surface. So this is the water surface here, and it will start from 0.9 to 1.8 meter below the water surface. Okay, and sidewall depth is similar, 3 meter. And the sloping here will be 300 millimeter horizontal, 25 millimeter vertical. And definitely there will be scraper. When the solids accumulate on the bottom, on the floor of the tank, it is scrapped. There are scraper, it is moved. Or it is removed from the system. Okay.
Yes, sir.
And again, this table, please don't try to memorize. This is just for your design information. You see, the typical SOR rate is given. Actually, this information, it is already given in text form. Here, there are for rectangular tank, the length, width, and depth are given. This is the range, and this is the typical value that you choose. And for circular, depth, diameter, bottom slope is given. The range and typical values that we generally choose for design purpose. And this is how we distribute wastewater in the inlet zone. Here, this is the multiple opening, because we know in rectangular sedimentation tank the main theme is we need to uniformly distribute the wastewater throughout the sedimentation settling zone. So these are the baffle valve, multiple opening, and it is uniformly distributed in the settling zone. And also another approach, flow is coming. There is a baffle. It is moving to downward, and then it will pass through the settling zone, because it must now here there is settling zone. It must pass through the settling zone, or multiple opening. Here it will pass again through the settling zone. Whatever is the approach, make sure that the wastewater passes through the settling, uniformly through the settling zone. Short circuit, for example, for short circuit, that means wastewater directly from inlet to outlet. It doesn't occur in your sedimentation. And this is the distribution, typical distribution figures. or distribution mechanism for circular tank. So this is side feed. That means wastewater, the main approach here in the rectangular tank, wastewater will be distributed in radial direction. So here the pipe is constructed at one side, so this side feed, or maybe the pipe is constructed, the pipe is constructed in the bottom portion that's vertical, or there is a pipe and there is baffle wall or multiple slot. So wastewater is distributed. Whatever is the approach, the main theme, it must be distributed radial. Okay, I think we stop here. It's already 9 p.m. and I have a meeting tomorrow to wake up early. Any question?
No, sir.
So we already took our last class test. So we don't have a class test. Inshallah, next week hopefully on the offline class we will meet in person. So next class we will start from this slide, isn't it?
Yes, sir. Inshallah.
Yes,
Inshallah,
sir.
and we already took our class test. So we will not be taking any class test before the midterm. Okay.
Yes, sir.
Yes, sir.
When did I take your class test? Last Sunday?
Yes, sir.
Okay. Okay then. Thank you. Good night. So tomorrow, remember, we don't have any class tomorrow. Okay.
Okay, sir. We will inform that to others.
Yeah, because today we just took a makeup class because we won't be able to take a class tomorrow. So this is the makeup class of tomorrow's schedule. Okay.
Yes, sir.
Okay then. So we will meet on maybe after the university open physically on Sunday. Okay.
Inshallah, sir.
Inshallah. Okay. Thank you.
Assalamu alaikum, sir.
Wow.